Hello students, we are back to part 3 of chapter 4. It's me again, Dr. Low. Now let's continue. Now question number 7. Consider the given function in piecewise. Plot the function, its odd periodic and even periodic expansions. Then compute its Fourier cosine and sine expansions. We look at the function given. This is a linear function. Fx equals to 1 minus x from 0 to 1. So when x is 0, we only need 2 points to sketch the line graph. When x is 0, the fx gives a value of 1. When x equals to 1, we get a 0. So from 0 to 1, we get this line, 1 minus x graph. Fx equals to 1 for 1 to 2. So this is for part 1. For part 2, we can extend from this graph. So to have the odd periodic, we need to reflect the graph symmetrical to the origin. So we repeat the same pattern. So same for the positive side of the graph. So this is the odd periodic function. Same for the even periodic extensions. We can extend from the original graph. So even periodic is symmetrical to the y-axis. So we only need to reflect the pattern of the graph on the y-axis. So the same pattern goes throughout the range of -6 to 6. So this is the even extension. Now we need to compute the Fourier, cosine and sine series. In this case, the range is from 0 to 2. As usual, we need to find the A0 and AN. Two over P. So 0 to 2. So calculation from here should give you the value of 3 over 2 . Now the AN. Here we need the integration by part. So this comes from the integral of by part 1 minus x cos n by x over 2. So calculation from here. The first term will return the value of 0. When we substitute 1 into the x, we get 0 here. We substitute 0 for sine term, we get another 0. So this whole term is void. So what is left is Sine n pi gives the value of 0. Sine 1 pi, sine 2 pi, and so on. They are all 0. So we're left with cos 0 is 1. Now we can consider whether n is odd or even at this point. It all depends on the possible values of n. So there are a few things we can take note here. Cos of n pi over 2 and the value of sine n pi over 2. When n takes the value of odd number, say 1, so cos pi over 2 is 0. When n takes the number of 3, cos 3 pi over 2 also 0. So it is 0 when n is odd. And when n is even, there are two possibilities. Okay, if we take a multiple of 4, let's say cos, when n equals to 4, cos 2 pi gives the value of positive 1. When n takes the value of 8, so cos 4 pi also 1. So when n equals to 4k, if k begins with the value of 1, and then if it is a multiple of 2, cos of pi is negative 1, cos of 3 pi is also negative 1. So when n is 6, cos of 3 pi also negative 1. So this is the value of n equals to 4k minus 2, where k starts from the value of 1, 2, 3, and so on. The same concept for sine n pi over 2. When n is even, 2, 4, 6, and so on, we get sine pi, sine 2 pi, and so on. So this will give the value of 0. When n is odd, there are two possibilities. When n is 1, we get sine half pi. Sine half pi gives the value of positive 1. When n equals to 5, sine 5 over 2 pi also positive 1. So we get a range of n equal to So this will give a list of 1, 5, 9, and so on. When n takes the value of 3, so 3 pi over 2 gives a value of -1. When n takes the value of 7, sine 7 pi over 2 also -1. So that gives a list of this is actually from the sequence of odd and even values. So say if for this case, we know that whenever n is odd, the cos of n pi over 2 gives a value of 0. When n equals to 4k is 1, 4k minus 2 is -1. So this is a range of even values of n. We know even values. And so on. So 2, 6, 10 will give the value of -1 when we substitute into cos n pi over 2. So this is for the range of n equal to 4k minus 2 when k begins with 1, 2, 3 and so on. While for the remaining 4, 8, 12, so this is for n equals to 4k when k begins with the value of 1, 2, 3 and so on. So whenever we substitute by the multiple of 4, cos will return the value of +1. So this is the idea of the list of even values of n. The same concept for the sine. We know that whenever n is even, the sine will return the value of 0, but it differentiates when n is odd value by +1 or -1. So the list of odd values, we have 1, 3, 5, 7, 9, 11 and so on. So for 1, 5, 9, this will return the value of +1 if we substitute to sine n pi over 2. So this is for the list of 4k minus 3 when k begins with the value of 1. For the case of 3, 7, 11, substitute into sine n pi over 2 returns the value of -1. So this is another group of odd values. So this will be for 4k minus 1 when k starts from the value of 1, 2 and so on. that is the entire idea. But we are not finished at this point yet. Now the intention is to summarize the an we obtained here from the complex function into a list of possible values. We can generate the potential values for n even. What are the potential values for an? So when we have 2, substituting into the function will return the value of So summarizing from here, we get substituting the value of 4 returns the value of 0. Substitute by 6, we get the value of Is the pattern clear? 2 over pi square, 0, 2 over 3 pi square. If it is unclear, you may continue the list. Get again a 0. When it is 2, 4, 6, 8, 10, when it is 10, so we can see the pattern now. 2 over 1 pi square, then 2 over 3 pi square, 2 over 5 pi square. So it is alternate from 0 when n equal to 4, when n equal to 8, 0 again. So again, if we repeat, we'll get another 0. So we can see a list of pattern. How about for n odd? The same concept. When n equals to 1, substituting into an, you will get substitute by 3, by 5, So we may see the list of patterns. We have 2 over 1 pi, 3 pi, 5 pi, 1, 3, 5. So it is alternate by negative, positive, negative, and if you repeat, you get a positive. So now we have a list of patterns. Putting the possible values of n even and n odd into an and summarize them into the Fourier cosine series. The A0 we obtained before this was 3 over 2. So 3 over 2 divided by 2. An cos n by x over 2. Now we have the potential values of an. So we did some work to summarize the an expressions just now. In the first table, when n is even, we see that we get a set of values in this pattern, 2 over 2n minus 1. This is for the odd number, 1, 3, 5, and so on. Pi square for the cos of n even number for 2, 6, 10, and so on. So to get 2, 6, 10, and so on, the list is this is the solution for the set of n even values, and for the set of n odd values, we notice the pattern of -1 to the power of n is to control the sign of positive negative. There is an alternate of negative, positive, negative. And this is for the cos of odd number of n, 1, 3, 5 and so on. So the odd number is so there is something which we can simplify from here. 4n minus 2 over 2. So we can simplify this term. So this is the solution. Thanks for watching. Drop a like, leave a comment, and don't forget to subscribe.